All right. Thank you everyone for coming. It's not very often that I get to play host. The reason I play host is that the intended speaker could not come because she had to go back to Brazil and get a permanent position, with short notice. So therefore, instead, I have the honor and pleasure to introduce Cristiane. And I'm assuming most people actually know who she is, but for the record, let me state that Cristiane is one of the PIs of the QuMat consortium. She will be the director when in the second period as well. Cristiane also is in some sense an academic stepmother to me because she was on my thesis committee a long time ago. So that makes it also even more fun to still be around here. She has a track record that's way longer than I can know, and so I will not even try to reproduce it. Instead, I will just give the words to Cristiane and looking forward to hear about practice.
Thank you very much. It is a great pleasure to tell you about our work on fractals. So we will see today how to go from metamaterials to real materials and what kind of things are at my heart at the moment. So most of the equipment that we have around ourselves are based on electronics. Everything is based on bits, ones and zeros. Ones means electrons are running. Zero means electrons are not running. Okay? So the behavior of electrons is extremely important. And we know that the electron's behavior depends very strongly on dimensionality. If we are in 3 dimensions, although Coulomb interactions are always there, we know that electrons behave like a firm liquid, which can be described as a quasi-particle with a renormalized mass and no interactions. On the other hand, in 2 dimensions, if we apply a perpendicular magnetic field, we see wonders like charge fractionalization, the formation of anions, excitations which carry a fractional charge. And in 1D, we have Luttinger liquids, where you get then spin charge separation. The system is strongly interactive. So density of states, interactions, the effect of impurities, all this is strongly dependent on the dimensionality. And here, all what I'm saying is about integer dimensions. So the question is, what should happen if we go in between, right? Can we then find the same between 1 dimension and 2 dimension? Are the electrons behaving like Luttinger liquids, like 2D, or completely different, or a mixture of both? When does it change and how does it change? So this is a very important question to understand electrons beyond what is already known. And here we are going to look at, for example, how electrons behave at 158 dimensions. So since this is a difficult problem, the first way that you approach it is by using the suggestion of when you have a new problem that you don't know what to do, you try to build a quantum simulator to understand that behavior. So the idea of taking nature in hands and building up systems in the way we want, it was proposed more than 60 years ago, but it took very long until people started using this idea to build something. The field started with cold atoms, where you use an optical lattice to simulate a lattice of systems, and you put atoms there, fermions or bosons. After a few years, it went into photonics quantum simulators, and the electronic quantum simulators is the youngest. This is one of those that we have been contributing a lot here in Utrecht. So I will tell you, first of all, that is now the outline of the talk. I will start reminding you about these electronic quantum simulators and the work we did in Utrecht in 2019, because this is considered to be the birth of a quantum fractal. Then after that, I will move into a photonic quantum simulator, and we will look at the dynamics in a fractal for photons now. And afterwards, I will come to the main new part of this talk, which is now a real material. It's no longer a metamaterial, so we go from quantum simulators to a real material. It's made of bismuth deposited on indium antimonite, where these structures emerge spontaneously. And I will tell you about our results that have been just accepted in Nature Physics. Okay, so first of all, I'm telling you about quantum fractals and what are fractals. Many of you maybe already know, these are these beautiful structures that most of the time exhibit the phenomenon of self-similarity. Here you see the Koch curve. This is the structure of ice. And here you see the Mandelbrot set is the solution of a mathematical equation. And to fix the ideas, let's start with a very simple one, the simplest you can imagine, which is the so-called Sierpinski triangle, where you start with a full triangle, you cut an inverted triangle in the center, you remain with 3 identical ones, the smaller than the initial one. You cut inverted triangles in those, you cut inverted triangles in the smaller ones, and so forth. And for this type of system, when you go to infinity, you are going to have a system which has 0 area and infinite perimeter. Looks very odd. So the system which has 0 area and infinite perimeter depends on how you are cutting. If you are cutting inside like this, you will run into 0 area and infinite perimeter. But if you have something like the Koch curve, the area remains finite. And you get the infinite perimeter because you are just adding segments around. It's an important difference, which means you not always go into 0 area when you go into infinite perimeter. It depends on how you do it. So one interesting property of fractals is that many of them have a fractal dimension, a no-integer dimension. And in the case of the Sierpinski triangle, the dimensionality is 158. The dimensionality is given by the log of the number, by the log of the scaling, and it comes like this. If you start in 1 dimension with a red curve, and now you scale it by 2, that's the 2 here, and you ask, what's the number of red curves I need to cover the blue one? The number is 2, I am in 1 dimension. If you start with the red square, you scale by 2 in the x and in the y directions, and then you ask how many copies of the red I need to cover the blue, it's 4. I am in 2 dimensions, that's the exponent. If I would have a red triangle that I scale by 2 here and by 2 here, and this would be a full blue, I would need 4 to completely cover it, but because it is a Sierpinski, I will need only 3. And log 3 divided by log 2 gives me the exponent, which is 158. Okay? So it's the number of copies I get after scaling, which is smaller than the usual ones I get in 2 dimensions. Okay, why should I care for fractals? First of all, nature is profoundly fractal. Not only Romanesco broccoli, the branches, the roots, and the leaves, our body is profoundly fractal. Everything in us is fractal. Our circulatory system, our neuronal system, our intestines, everything that needs to exchange process has the interest to be fractal. There are also dynamical fractals. Our heartbeat is a fractal. And it's extremely important that it's a fractal. If it becomes completely periodic or completely chaotic, we die. It has to be a fractal. Notice that if you look here, the heartbeat at 3 minutes, 30 minutes, and 300 minutes, you say, I don't see the self-similarity as you could see with the Sierpinski triangle. This is a fractal in a statistical sense. If you look at all the distributions and so, you will see it is a fractal, okay? But not a mathematical fractal like the Sierpinski. Okay, in addition, fractals are extremely interesting for technology because if you cover a 2D surface with a fractal for building a solar cell, more you increase the complexity of the fractal, more energy can store per unit area for the same surface. If you do an antenna with a fractal, you have a small and large length scale, so you can send and receive large and small frequencies simultaneously. It's extremely useful. And of course, they appear to our senses as being beautiful because it's nature. And our senses are used to identify everything that looks like nature as beautiful. So they were used in arts, for instance, much before they were understood. This is from the 11th century. It is a church in Rome. Escher has been playing with them quite a lot. This is a hyperbolic space projection on 2D, and as you approach the horizon, things get smaller and smaller. And this is a painting by Pollock, who was dancing on top of the canvas, and by controlling the density of the things that he was pouring, he was forming fractals underneath. So in science, the first fractal, in the 80s, people were studying classical fractals, and there was lots of activity right after the work of Mandelbrot, S.J.M, Bach, Alexander Kadanoff. Many of them studied classical fractals. But into the quantum realm, things started only much later. In 2015, a paper in Nature Chemistry has shown how to build fractals using aromatic bromocompounds as building blocks. But they have built it and they stopped there. They did nothing with it, okay? And one question that I had for very long was the following. If I build a fractal and we put electrons in it, do the electrons know that they are in a fractal? Because after all, I am not going to be able to build something that goes to infinity when you would have a true fractal. So I have to stop on a small generation. When I stop, there will just be a few holes. Is this enough for the electron to understand that this is a fractal or not? Do they sense it as a 2-dimension or as a dimension 158? That was the first question that had been disturbing me for very long. And that's why then, when Sander Kempkes was doing the PhD in my group, we decided to calculate all this and to make a design that then Marlu and Ingmar could build in the lab of a fractal for electrons. So we then did the following. We are going to use a technique that has been pioneered before. You take a metal like copper. On the surface, there are floating electrons in 2 dimensions. They form a 2D electron gas above a certain threshold energy. Now you deposit adsorbates, like for instance carbon monoxide, hundreds of them. And with the tip of the S.J.M, you control the precise position with atomic precision where you are putting them. So they are going to confine their structure. They are like mountains. The technique was first made in the group of Don Eigler. And this, you can see here, it built what is called a quantum coral. It's one of the most beautiful experiments ever. Each of these atoms here is one atom of iron. They are separated by 1 nanometer. And the waves that you are seeing inside are the electronic wave functions. It's modulus of psi square. Okay, and because it's in the nano domain, it's called a quantum coral. Instead of having the water-making waves, you have the electronic wave function. After that, they did this very beautiful video, which is called A Boy and His Atom. You can see it on YouTube. And it's the smallest video ever made. Each pixel is 1 atom, as you can see there. So the technique was built in 93, but it took almost 20 years until Harry Manhattan, who had been a student of Don Eigler, to say, okay, let's put 2 quantum corals together and open the door in between. And I can control this door to be less open or more open. And now each of the sites acts as an artificial atom. So it's a site for my electrons. And my electrons will hop. And now the hopping is controlled not by how far the 2 sites are, as it's the usual case in solids, but how open the door is, because each of these black things around is a mountain. Okay, so I am constricting the quantum dot here, and this separates the energy levels by a time. So Manhattan then did this to build graphene. Here you see, this is two decks on copper 111, the yellow. The brown ones are the carbon monoxide. And he came, and with the tip of the S.J.M, he took them one by one. He patterned a triangular lattice. And by patterning a triangular lattice, the electrons are forced to go around. So the electrons are forced into a honeycomb. And if you look now here at the local density of states, if I don't tell you that this distance is 2 nanometers, and if you would think it is an angstrom, this would be a perfect graphene. It is just a perfect graphene made by hand on a scale that's 10 times larger. But it's super nice because now you can compress or dilate this structure, and you can make PN junctions and so on. So it is a way to build perfect lattices on the nanometer scale. But when he built it, there were two things. He's patterning a triangular lattice on top of a triangular substrate, because copper is triangular. And you can only put the COs on top of copper. The question is, can I also pattern other kinds of lattices which are not triangular or honeycomb? Because if I can only do this, I don't go very far. And that's something we have been doing. We did lots of works in this field with Swart and Daniel Vanmaekelbergh here. But today we will use this technique to pattern the Sierpinski triangle, which is again a triangle, so it's very easy. And we are going to build 3 generations. And this is the experimental setup. So this is an image taken, a topographic image taken at 1 volt and at this current. And you see, by confining the structure by these walls and putting now some barriers in the center, I hope to build these 3 structures where now these colors, red, blue, and green, are the sites where the electrons are going to sit. This is for the first generation. And I have these colors differently because red sites have one neighbor, green sites have 2 neighbors, and blue sites have 3 neighbors. Okay? So I have sites with a different connectivity. And so now you can do a very easy model that's called muffin-chun. You basically solve Schrödinger equation for this type of barriers, and you know what's the effective electron mass, you know the height of the barriers, you know the diameter of the barriers, and you solve it. And now you also try to have this continuum model described by a tight binding approach, and you match all the energy levels to understand the size of the hobby. Then you come on your sample, this is a 3rd generation one. You sit at each of the red, blue, and green sites, in many of them, and you take the spectra. You take GIGV, and you compare it with the GIGV of the copper, and you get curves like this. And you can now compare these curves to our calculations, and you get something like this. So the model can describe the experiment, especially in terms of where the main peaks are and so on. So now you select for this GIGV 3 values, one when all the 3 are the same, and one when red is low, blue and green are high, or blue and green are high and blue is low. And for those fixed values of voltage, you come and you scan, so this is minus 300, minus 200, and minus 100, and you scan the entire sample. So what I'm plotting here is modulus of wave function square. And you see that very light means very high peaks, and yellow means lower peaks. So here you see a bonding configuration, an anti-bonding configuration, and a non-bonding configuration. You see this one is pretty much like the ones that the Chinese were building with the bromo. And underneath you see the calculations that they agree very well with experiments. Okay, this is good, but the main question that I had was, do the electrons know that they live at fractal dimension? And for this, you now are going to use something which is called the box counting. In the box counting technique, you are going to create some circles or some boxes of a certain size, and you cover all the white parts of your local density of states. And for a certain radius, you look at the number that you obtain, log of the number as a function of the log of the inverse radius. You count 1, 2, 3, 4, 5, you get a dot here. Now you make your box smaller, you count again, you get another number, smaller and bigger. And all these dots are going to sit over a straight line, which tells me what is the dimensionality of the object that I'm covering. So the modulus of psi squared here has a dimensionality, which is this slope, which is 159. Okay? So this means the electrons know that they are living in dimension 159. Now you can do it for all the energies that you have. You see it doesn't work very well for the one at -100. That's the one you had blacks and whites for the anti-bonding configuration. But it works very well for all the rest. And if you do the same technique for a square lattice, you see you are always below it. Okay? So it is amazing that with a system of a few holes, the electrons already know that they are in a fractal. That was a big surprise. So we were very happy when this paper has been selected as one of the 15 highlights to celebrate the 15 years of nature physics. It was selected as one of the most important publications by them in the last 15 years, and it was featured in that work. Okay, so by patterning CO copper 111 in the nanometer range, we have shown that the electronic wave function fills the fractal dimension. Good. This electronic quantum simulator was good to see statics. Now, what about dynamics? For dynamics, we need to go to a different technique. And I was then visiting China in end of 2019, just before COVID. And I have seen the work that Xiaoying Xu was doing. She was doing measurements in fractals. And then we got together to do this next work. I like to call this work the quantum ant in the labyrinth. Because S.J.M used to say that the diffusion of a classical particle in a fractal is the problem of an ant in a labyrinth. You put in the ant in the labyrinth, where does it go? Now we have a quantum ant, okay? So, what is it about? It is the following. It is the following. You take a chip, and then with a laser, you do what is called the femtosecond laser direct writing techniques. You are going to create waveguides inside your chip. These are the waveguides in pink that you are creating, and the black is the end of your waveguide. Okay? The cross-section of these waveguides is going to form a fractal. And then what you are going to do, you are going to inject photons in these wave elements. The photons travel along the peak region with the velocity of light. So the length of this waveguide divided by the speed of light gives you time. And you are going to build hundreds of this, each one with a different length, because this is going to partition time for you. Okay, so really hundreds of them. And the photon will then move along here with the speed of light, but at the same time, it will hop via quantum tunneling from one circle to the next. So these lines here don't exist. They are just guided to the eyes, though just the circles exist, and this is the cross-section of my waveguides. Okay? So, to make sure that the results we are going to get are not biased, we will not only investigate the Sierpinski triangle, but also the Sierpinski carpet. The Sierpinski carpet is something that if I take this structure and I scale it by 3 here and by 3 here, I am going to get 8 copies. The central one is missing. So it's log 8 divided by log 3, which means it has dimension 189. Okay? And in addition to the Sierpinski carpet that has dimension 189, we also investigated the dual Sierpinski carpet. What is the dual structure? The dual structure, you take a completely solid region here, which is this blue one, and now you put a dot in the center of the solid ones, and this is the dot here. So you will associate dots to the points which are solid both in the previous structure. And when you build a dual Sierpinski, it has the same fractal dimension as the Sierpinski, but the distribution of holes is completely different. So by investigating these three structures, we are able to understand how is the behavior at different fractal dimension, and at the same fractal dimension when we have a different distribution of lengths. So this is then the experiment. What you do is you inject at the top, and you detect at the end that is entering here into the plane. Each of the lengths that you do is one time here, in this propagation length, okay, that's from the roll of time. And then you measure the variance, the mean square displacement, which is given here in red in the experiment and in blue in the numerical simulation. So you see two things. Usually you have diffusion. What do you expect from diffusion? It starts with t squared when it's ballistic, and then it goes linear in t if it is diffusive, like the Langevin equation that we have seen yesterday. So here it's starting with t to the 2.5 instead of the t squared. Why is it so? It is so because I'm injecting from the corner. If I would be injecting, if I would take a triangle and inject in the center that the particle could go everywhere, it would be t squared. But because of the corner, it's 2.5. It would be the same for a full triangle. So it stays as 2.5 up to the point when the light at 2.675 here, the length is this. The photons have met the first big hole here. At this point, it starts deviating from the 2.5. And at 3, so the photons have to go around the hole, they can't proceed. And when they can propagate again, this is this point, 3.875 millimeters, they are picking up here an exponent, which is precisely the fractal dimension of the object. Okay? It goes like this until this point, 9.275. I don't know, this beam is not so good. Maybe there in the back you can see better. When now the photons have reached the entire sample, then it saturates. So then here, what happens is that if you do yeah, we tried already, it doesn't help with the quality of the humor. So here you see we can reproduce the same thing by doing these tight binding calculations. Okay, is this a coincidence or is this a generic behavior? And one very important aspect here is this exponent, the fractal dimension that we are obtaining, is different than what's predicted in the classical case. Classically, it's predicted that the spectral dimension divided by the fractal dimension. So we are getting something different than the classical case. What if we now investigate a different one? Yes.
What is the spectral dimension?
Yeah, the spectral dimension is something that qualifies how your spectrum is. It's one of the dimensionalities that can be associated to a fractal. Okay? So then you can now come to the Sierpinski carpet, and you will see that now it's going with 2.4. It's slightly different than the 2.5. And it's so because it's now a square at the corner that I'm injecting and not a triangle. And again, the same thing. At 3.85, it deviates from the 2.4. It's where light has met the first hole. And after it went around the first hole and can propagate again, it's picking up the exponent 1.89. For this one, we couldn't, it's a very big sample. We couldn't go until the point when it really goes through the entire sample to saturate, but the behavior is the same. So from here, we conclude that from the moment when the photons see the first hole, they understand the dimensionality of the fractal, and they pick up the fractal exponent. Is this really confirmed for the case of the dual one? So for the dual one now, when you inject here, it immediately meets a hole. So now it immediately starts with 1.89. Yes?
Why do you have this kind of tiny oscillations?
This is experiment. So when you inject your photons, you have a very tiny waveguide, and you are supposed to inject it very, very perpendicular for not scattering at the boundaries. But this is very difficult. Sometimes you are not able to get it fully parallel to the walls, and then you get some noise. That is basically it. Yes?
Could you also comment a bit on what you mean by classical situation here? I mean, should I think of a classical particle now hopping randomly around in the fractal, or is it something else?
So, no. You should think about, that one, the classical there that I had, the classical law is the ant. It's the ant moving in this system, okay? Which is different. So now you would say, okay, but these experiments with the waveguides are classical simulators. In a way, they are, but they simulate a quantum mechanical equation, which is Schrödinger equation. So if you look at the equation that the system is obeying, if you take the z direction as time, okay, this is a paraxial equation. It is a classical system which serves as a quantum simulator. So it's Schrödinger, it's not Maxwell. Okay, so in that sense, it's quantum. Okay, so it looks like that every time when the photon meets the first hole, it already knows the fractal exponent of the structure. This was a big surprise for us. And then, after that, I went on to our UU outreach sector, and I gave this interview to the conversation about this work. And I wanted to be very provocative and to tell people the following. 30 years ago, Roger Penrose has been proposing that processes in the brain move according to the laws of quantum mechanics. He has been beaten to death because everybody was saying, forget it. How could it be quantum? It's room temperature. You would lose phase coherence extremely fast. It's impossible. Nobody would have believed. So in 1980s, to get a quantum Hall plateau, Klaus von Klitzing needed to go to 4 Kelvin to get a very dirty, ugly signature of a quantum phenomenon. But now things have changed. So we know that the neurons form a fractal structure. So the fractal dimension of the neuronal structure in the brain has been measured 2 years ago. I don't know if it's 1.68 or 86. But now the question is, should then the dynamics in this fractal of the neuronal structure be classical or quantum? Let me tell you a few thoughts that I have on the topic. So graphene, just a two-dimensional brain, the same quantum Hall effect that was measured at 4 Kelvin for gallium arsenide has now been measured at room temperature in graphene, 300 Kelvin. Okay, beautiful plateaus. We have quantum effects at room temperature, well defined. You will tell, okay, but there is a magnetic field of 29 Tesla. I don't have 29 Tesla in my brain. Well, we have also seen that if you have curvature in graphene, you might have pseudomagnetic fields of 300, 400 Tesla, just the curvature, okay? This is the experiment by Fremling in Science in 2010. So I don't have real magnetic fields, but I could have pseudomagnetic fields. And on top of it, the neurons are made of carbon nanotubes. So carbon is very light, has a very light spin-orbit coupling, very small, but when you curve it, the spin-orbit coupling increases significantly. Leo Kalvenhoven has been measuring that. So it could be that topology is playing a very important role in the brain, in the transmission of all the information. So given all these experiments that we have seen in the last years, I don't dare to doubt that transport in the brain could be quantum. But what I'm saying is, we have a law. We know how a quantum particle would diffuse in the brain. The exponent is just the Hausdorff dimension instead of the spectral dimension divided by the Hausdorff dimension. So go and measure and compare with the classical and the quantum. And we will know whether it's quantum or not. Okay, so now one needs to get the biologists doing the work. So that was this interview, very provocative. It called lots of attention. It has been the most seen interview in the conversation during COVID, beating all the COVID results. from UU, the most seen from UU. And it was translated also in Spanish. It was the sixth most seen in Spanish. Okay, now, what about topology? So again, if you look at the tenfold way, so topological insulators are these materials which are insulating the bulk and metallic at the edges. They have been classified in terms of the symmetries and the dimensionality. Again, we know everything for non-interacting ones, but it is all integer dimensions, but there are real numbers in this world. What happens when I go in between? This one is not topological for the same class of symmetries. This one is topological. When does it change? Is it infinitesimally after 0? Is just before 1? Or is in the middle, completely different, something else? Okay? So this table, this tenfold way, has been now been generalized by people who are studying topology for the case of non-Hermitian systems, interacting systems, non-equilibrium systems, you name it. But there are two generalizations that are very important, even at the single particle level. The first one is what happens here in between for non-integer dimension. And the second one is concerning symmetries. That is another part of the research that Anwar and Lumen are doing in my group. For instance, when you go from here into the topological crystalline insulators, it can be that you look at the system and you think there are no symmetries there, but they are hidden. There are latent symmetries. So this is one of the things that we are looking to go beyond the very obvious symmetries which are visible to us. And the second important part of the research in my group is when you go in between dimensions. Okay, so these are the topological studies in fractals. It started with photonics since 2020. They have been doing, again, quantum simulators. If you now take your waveguides, the pink lines that I have been showing you, and you spiral them, this acts like electrons in a magnetic field. They start rotating, right? So that is a way to simulate quantum Hall effect and anomalous quantum Hall. It was also in 2022 investigated in acoustic metamaterials, but now we have the very first real material which shows fractals and fractal dimension and topology. So this also started in 2019 when I visited the Shanghai Jiangtong University. This is the group of Jifeng Jia, and this is Shen Liu. Shen Liu had been depositing bismuth on Indium antimonite, and then, depending on how long she cooks, how fast she changes the temperatures, how long she lasts, she gets this. And I was highly excited when I have seen. So she gave the data to us. First, she had some collaboration with someone calculating GFT, and they thought the samples are not topological, but it was wrong. It was published there. And basically what happens is you have indium antimonite, then you get a wetting layer, then you get Sierpinski triangle being formed as one layer bismuth on top of the wetting layer. And sometimes you get a film of bismuth on top and another fractal in the third layer. That's how they go. And now if you look at that, so these are some of the examples, and you can now do spectroscopy along this edge of this one. And you will see that your wetting layer and the substrate is in black, there is a big gap. The wetting layer has this gap of zero bias. And now when you start scanning everything here along these dots, you will see this turquoise here is the last one at the border. You see a zero bias peak at the corner. So this is a strong indication that this system is topological. And we went then working on that. That was the master thesis of Robert Vanmaekelbergh, who was here in my group. So most of it is his master thesis, and then he continued working on it to include disorder. And Rodrigo was his daily supervisor for this work. So basically here we are now adding the effect of spin-orbit coupling into his Buntington model, and then afterwards Lumen did for the together with Robert for the type 9. Okay? So this is an example of the third generation. Let me show you the results. Into this pink column, you have the results if you have only kinetic terms. If you now introduce the intrinsic spin-orbit coupling, this is the middle column. And if in addition to the intrinsic spin-orbit coupling, you introduce Rashba, that's the last column. Okay? So you can see the following. Those ones in pink you had already seen before. The bulk phase with the bonding, there is a non-bonding and the anti-bonding that I have shown in the work of Kempkes. Now when you get a strong intrinsic spin-orbit coupling comparable to the kinetic term, you see here something has changed. Before the red and the green sides, so red are corners, green are sides, and blue are bulk. Before the red and the green had a peak, now the green has a dip. Only the red has a peak. So this means I am going to have these corner modes here at 0 MeV. Okay? So you have the bulk, and at 0 MeV, the big red one are the 0 ones. And as you keep increasing, you then see edge modes at the outer edge and edge modes at the inner edge. These edge modes are driven by the intrinsic spin-orbit coupling, so they are topological. This is the first quantum spin hole, topological insulator in a fractal. And now if I put Rashba, I destroy the effect, as I expect, from the K-Miller model further. The effect is gone in the presence of a Rashba. I get back to have the peak red and green precisely as I had before putting intrinsic. Yes.
Finite temperature or is that 0 temperature?
No. So this is the measurements are done at 4 Kelvin. Okay. And the calculations are 0 temperature. The only thing we have is the broadening due to scattering with the bulk. Okay. So I am showing you just the tight binding calculations, but the tight binding, no, the muffin chain calculations, but we did also the tight binding. And now bismuth has p orbitals also. So the tight binding have to take s, px, and py orbitals into account. And the bulk part of it is triangular for this type of substrate. Okay, now how does this compare to the experiments? So here on the top you have the experiments, and at the bottom you have the muffin chain. What you see is the following. Deep at minus 500 MeV, very deep down there, you will have a bulky phase. The pink is high density of states, high peaks. It is all in the bulk. Then it starts partitioning. Here it makes some blobs. That phase doesn't agree so well with the experiments. We'll come back to it later. And around 0 energy, I see the corner modes. Here I also see the corner modes. The right one is missing. Then around 100 MeV, I see the outer edge in the theory and in the experiments. And around 200 MeV, I see the inner edge, theory and experiments. And then it's a mess because it's higher orbital. Now, how is the effect of disorder? We investigated 3 types of disorder. In the first case, you start mixing up parts of your Sierpinski triangle to see whether your phases remain robust. So in this messy structure, you can see that you still have your bulk, you still have your edges, you still have some corners here, here again edges, and so on. So the phases that existed before are robust to the disorder. They still exist, okay? Here, we are now changing the height of the barriers that are confining my structure. And you see, again, the bulk, the edge and the corner are robust. In this one, you are making a mess in the pixels where you are putting the sides. This one is the most damaging of all. But it's still, you still see the edges, you still see the corner modes and the edge. These samples are amorphous, 40% disorder. So the system is extremely robust. The features are extremely robust. Now we did another type of disorder. First, we took now an edge that was a straight edge, not atomically resolved as before, but straight, like this. and we rotate the sample within the box because you get an interference effect. And when you do that, look, now that phase that the blobs were not so clear, now you get the 4 blobs, precisely as in the experiment. And you get the 2, and you see that this one disappears because of interference. And you see that this painted one here is also painted there. And for this type of case, we even get a quantitative agreement for the energies where you see each phase. Not only we get the full sequence of phases that you see in theory and experiments the same, but also the energies at which you see them. So we had a very good agreement. Let me tell you one little thing. I don't know how I'm doing with time.
Let's say if you can finish up within 10, then there can still be questions.
10 minutes is perfect. Yes. Okay, let me show you one funny thing. I don't know if you noticed that there are these light blue. Light blue means very low energies. Around these samples at very low energies. Let me show you a different one. So this is another sample. And now you do the local density of states. Blue means low energy. You are starting at positive plus 600, and you keep lowering and lowering. And look at that. What's the most prominent feature that you see here? The most prominent feature that I see are these blue lines that they look like they are drawn by hand. It is super sharp. We are at minus 500 MeV. They are there already from minus 400, minus 350 about. You start seeing super sharp lines. But these are not the edge modes that we are used, because the edge modes would be pink. They are depleted modes, sharp like hell. We also obtain them in the theory, but I don't know what they mean. Okay, we get them in theory and in experiments, but I don't know what they are. They might have some topological nature, because it's impossible to get something with this level of precision in a measurement if it's not extremely robust and protected by something big. I think this is a very interesting thing to further studies. Okay, now you would ask me, I will just give you some taste about the last works that have been done in the group. Until now, I told you only about non-interacting systems. I have put a strong intrinsic spin-orbit coupling in the last case for the topology, but it's still a one-body term. What now when I have interactions at fractional dimensions? So this was the master thesis of Monica Conte in my group last year. And the paper is now submitted, just came back with 2 very good directory reports, so we are very happy about it. So this is the system that we have, that we are analyzing for a Hubbard model. And now, basically, this is like a flake of graphene where you have a missing black here in the middle. And because it is a flake, it is very important that you get 2 ingredients. First, you don't have the same number of sides for the A and B sublattices. So you have a lattice where the number of A and B sublattices is different. And second, you have a lattice for which you have sites with different connectivity. So what we have learned by lattices is different. It's 2 tiny differences, but it gives a lot of difference. Because now, so Monica has been doing quantum Monte Carlo exact diagonalization in mean field studies of this problem, and she found something that Hubbard himself has been looking forever. So Hubbard could never find a phase that was magnetic and metallic at the same time at half healing. If you dope the system, it's a different thing. But if you are at charge neutrality at half healing, every time that it was metallic, it was insulated. That it was magnetic, it was insulating. And if it was metallic, then there was no magnetism. Okay? But by now, by having these hexagons in the flake forming a fractal that is different from the usual hexagon, what we are going to see is that we get a ferrimagnetic phase. So So you have spin up and down, but they are in balance. The size of the up and the down are different. And this phase is metallic. So it brings you lots of new possibilities just by modifying slightly your system. Okay? And what is interesting is that the critical Hubbard parameter for which you go into from the paramagnetic into the perimagnetic phase is the same as you would have for the 2D honeycomb. But the phase you go in is different. The other one would be antiferro. And now here you get to the ferimag. Okay. Another thing that we have been doing just to make a publicity for the work, the collaboration with Marcus. I was in his PhD, I was the expert in his PhD defense. And then I was asking him a question, and this has been bringing us into this collaboration. So we have been now creating no-Hermitian systems such that the nodal lines form a fractal, okay? And this means these are the lines where I have zero energy. This is my fractal band structure in my fractal Fermi surface. So we could create these models for 2 bands and 3 bands and so on in K space. And now this white region here around is my Fermi surface. So imagine maybe what could happen to all these phenomena which is Fermi surface driven, like pairing. I will get Cooper pairs in a fractal. Do I get self-similar Cooper pairs? Different sizes. What would happen with the charge density wave? I would get beatings because the charge density wave will have different nesting vectors. So there is a space for lots of stuff. And also here, the first surface is the red. Look, I can get nesting now outside the Fermi surface, taking outer parts from my Fermi surface across these circles. There is a space for lots of imagination. So this is for the no-Hermitian. The previous one was for the on-site interactions, something that's going on for years now, and Robin has been working on it very heavily and waiting for the experimental results for long, is the collaboration with the group of Florian Schreck, on which they are using optical tweezers to build a fractal lattice with Rydberg atoms, and now we get long-range interactions. And then you ask yourself, how can you handle structures which have no translational symmetry? Numerically, you need extremely enormous system sizes, and that's what Robin has been doing a lot, looking at symmetries at the level of the Hamiltonian to simplify the problem in a way that it becomes sparse matrices and you can handle it while we wait for the experimentalists. I have the quantum chaos game. Has anyone here who has never seen the quantum chaos game?
I have never seen.
You have never seen? Okay, so then I show you. Our friend Einstein has been saying that God does not play dice with the universe. So now, let's look at that. We are going to play what's called the quantum chaos game. So the quantum chaos game is the following. You will draw a triangle. You can find it in the YouTube also. You draw a triangle. And now, let me stop this for a minute. In this triangle, you will now choose a random point. Anyway, it can be inside, it could even be outside. But choose one inside, it's easier. Because otherwise you have to neglect everything else outside. And now we are going to call these vertices 1, 2, 3, but because my dice has always 6 numbers, let's say 1, 2, 3, 4, 5, 6. Okay? And now we are going to play dice. So you pick up a random number, you play dice. Which number do you get? 3. So 1, 2, 3, here. You will connect your random point to the vertex number 3. And then you choose the middle point of your segment and erase the rest. Play dice again. Get 1, connect to the vertex number 1, choose the middle point. Okay? We'll play this game many times. A random game. Choose a random point, play dice, Got number 2. Choose the middle point between a random point and the vertex 2. Play dice again. Got 4. Choose the middle point. Got 2 again. Choose the middle point. And then you let your computer simulation run. After a few thousand, you got a beautiful fractal out of a completely random law. Isn't it beautiful how you can go random and get something that is structured? Okay, I come then to my conclusions. I have been revising you this work we did in 2019 about how to realize the first electronic quantum fractal. Then I have shown you how to study the dynamics in a fractal using photonic quantum simulators. Finally, I told you our last work for bismuth on indium antimonide, where fractals are spontaneously formed, and how are the topological properties in the system. I gave you a glance on our work on the fractal nodal band structures in the fractal-lattice Hubbard model. Before I finish, I need to acknowledge all the heroes. These are the young people, the wonderful people with whom I had the pleasure to interact. Sander was the one doing the calculations for the first quantum fractal. Luke was doing the experiments under Ingvar Zwart and Daniel. Xiao Yushu was doing the numerical simulations and the experiments for the photonic fractal. Shen Liu was doing the samples and the S.J.M experiments for the bismuth fractal. Robert, during his master and beyond, was doing the theoretical calculations, also under the supervision of Rodrigo. Leuven has been doing the tight binding calculations for this work with Robert. Monica was co-supervised by Vinicius for the quantum Monte Carlo, especially in Malta, has been contributing a lot to understand the latent symmetries in the fractal structure. And the ones here under, I didn't tell you about their works, although they're doing great stuff also. And it's the rest of the team with the youngest one, which is Zeb. So with this, I offer you a fractal flower, and I thank you very much for your attention.
Very nice. There's time for a few questions before we break. I have a question then while we think. So you enticed us with your anti-states in these experiments where you go to very, very low temperatures and you don't see anything.
Yeah.
Right.
Well, I see a depletion.
You see depletion.
Depletion in the density of states, right?
So
you see here, you see a very strong depletion. And it's robust in a very long range of voltages. And the same for the experiments.
Right. So the closest thing I can come to think about is what would happen in the lead lattice, for instance, where you have exact cancellation. But then it's only for exact points, which leads to localized states.
Yes.
This would not work here. Right?
No, it wouldn't, because the lead lattice is precisely this latent symmetry. These are the sites at which the destructive interference is perfect. But those sites are not. And the lead lattice, where you have the destructive interference, you always have at any voltage. That's why you get a flat band from the edge states. But here not, because at other energies you have other densities. So it must be something else.
There was a few questions during the talk as well. Is there anyone online who would like to? No.
Ask. They are discussing among themselves at the end.
Yes. Lars, share your thoughts.
Share your thoughts.
Yeah, I was just thinking, to me it sounds like it's just boundary condition. Like if you have particle in the box, there's nothing at the boundary.
No, your box is much larger. You see, the box is the black thing.
No, but the
In the
atoms
boundary, but it is only here at negative energies.
that's
So
the lowest energy.
the experiments don't have any boundaries. The sample is gigantic and you are probing locally on a very tiny thing. So for sure, this cannot be any effect of boundaries because your boundaries are further away experimentally. And also theoretically, we have also played with the boundaries, different larger.
Those boundaries.
Yeah, you can take larger boundaries, different shapes of boundaries to see how robust the results are. And they are robust.
The fractal boundaries.
The fractal boundaries.
Yeah, the fractal boundary, yeah, but it's only there for negative energies. Again, it's not there afterwards. It disappears. And then when you come, for instance, here, you have a completely red, pink density of states. It is a feature. It's for sure a feature. Because you see it repeating every time you measure it. Look here. Look, all the energies. No, it is. You see how things are evolving, and you are having here the edge modes for the little triangles. You see, here you see boundaries which are pink, but then also connected to the other things. And then suddenly, you see the blue. I have been talking to many people about it. No one has any idea. And the bulk is also super well defined. Inside, constrained by this blue. So if it would be any kind of interference, it should happen also at other energies, right? And it's robust to different types of samples, the sample that you take for calculating. Yes.
Yeah, I was wondering about the concept of dynamic fractals.
Yes.
So, is this a fractal in time? But is it a fractal in time?
Yeah. So no. The fractal is a real fractal in space.
Yeah.
So this is the fractal. Let me show it for you here. You see the
No,
first section.
No, the concept of dynamic fractals that you just mentioned in the beginning when you said that heart springs and
Yeah. Yeah. So the heart beating, the dynamic of fractal, that one. The heart beating, if you look at the statistical features at 330 minutes and 300 minutes, they are self-similar.
Okay.
Okay?
And okay.
So in that sense.
I mean, as an allude, I just recently started wearing a sports watch, and it's actually trying to tell me what my heart rate variability is, which is the same idea. And it's actually saying if the heart rate is too regular, that's a bad thing. It surprised me a lot.
Yes, that is it. Yeah.
Okay, then without further ado, I think we thank Cristiane again.
Okay. Thank you.